For as long as human beings have looked toward the sky, the sun has seemed almost impossible to hide. It rises above every horizon. It floods the daytime world with light. Its warmth reaches across nearly 100 million miles of space before touching your skin. And with modern telescopes, we have watched dark sunspots drift across its surface, seen towers of plasma rise higher than the Earth, and followed violent eruptions as they raced outward into the solar system. Spacecraft have photographed the sun in visible light, ultraviolet radiation, and X-rays. One probe has even flown directly through its outer atmosphere, passing closer to our star than any human-made object before it. And yet, until very recently, there was still a region of the sun that humanity had never truly seen: its poles. Not the way we see the poles of Earth in maps and satellite images. Not from above, with the entire region spread out beneath us. From our usual position near the flat plane of the planets, the solar poles have always remained close to the sun's distant edge, distorted by perspective and partly concealed behind the curve of the star itself. For centuries, the south pole of the sun was less like a known place and more like a missing piece in our view of the solar system. Then a spacecraft called Solar Orbiter began to change its path. Slowly, using the gravity of Venus, it climbed beneath the familiar plane where Earth and most of the planets travel. With each carefully planned encounter, its orbit tilted farther. The southern regions of the sun began to emerge from behind the brilliant horizon. And in 2025, humanity received its first clear look toward the sun's south pole. What appeared there was not the simple, orderly end of a giant magnetic field that scientists might have hoped to find. Instead, the pole looked divided. Invisible magnetic fields, translated into colored scientific maps, revealed patches of opposite polarity crowded together in the same region. Areas belonging to one magnetic orientation were tangled with areas pointing the other way. The sun's south pole appeared to be north and south at the same time. It was as though the star had temporarily lost its magnetic identity. But this was not a wound in the sun. It was not evidence that our star was breaking apart, nor the beginning of some sudden catastrophe. It was something quieter, slower, and perhaps even more remarkable. The sun was rebuilding itself. The magnetic structure that had governed the previous years was fading. Fragments of an older solar cycle were being erased, carried away, or canceled by fields moving in the opposite direction. At the same time, the foundations of a new magnetic pole were beginning to gather. What Solar Orbiter had captured was not a finished transformation. It was the sun, caught between two versions of itself. Far below the glowing atmosphere, enormous rivers of electrically charged gas were continuing to move. Across the visible surface, dying sunspots were leaving behind fragments of magnetism. Those fragments were being pushed, scattered, and slowly transported toward the poles, where they would help determine what the sun would become next. Above the South Pole, plasma rose into an atmosphere heated to extraordinary temperatures. Some of it fell back. Some may have escaped outward, joining the solar wind that surrounds every planet, including our own. And hidden within this restless region was a question that reaches far beyond one unusual image. How does a star reverse a magnetic field that stretches across millions of miles? How does an old pole disappear? And how, from a chaotic mixture of opposing forces, does the sun quietly create a new one? To understand what is happening at the South Pole, we must first understand why this place remained hidden for so long. Because although the sun illuminates almost everything around us, the geometry of the solar system has kept us looking at it from nearly the same narrow angle for our entire history. And to see beyond that angle, a spacecraft would have to leave the flat world of the planets behind. From Earth, the sun appears to move across the sky each day, as though it were presenting its entire face to us. But in reality, our view is far more limited than it seems. Earth travels around the sun inside a broad, nearly flat plane. Most of the other planets do the same. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all follow paths that remain relatively close to this shared celestial surface, known as the ecliptic plane. You can imagine the solar system as a vast, thin disk. At the center is the Sun. Around it, the planets circle like small beads moving along neighboring rings. Although their orbits are not perfectly aligned, most of them remain close enough to the same plane that they observe the Sun from roughly the same direction, near its equator. This creates an unusual limitation. We can watch features rotate across the Sun's face. We can follow sunspots as they emerge on one side, cross the visible disk, and disappear around the other. We can study eruptions near the equator and at middle latitudes with extraordinary detail. But the poles remain pressed against the upper and lower edges of the solar disk. From our perspective, looking toward a solar pole is like trying to study the top of a spinning globe while standing almost level with its equator. The farther you look toward the pole, the more compressed everything becomes. Distances appear distorted. Structures overlap. Features that may be separated by thousands of miles can seem to sit almost directly on top of one another. It is similar to trying to read the face of a clock while looking at it from the side. You may see the rim. You may catch the movement of the hands, but you cannot easily tell where each hand is pointing or how the pattern is arranged across the full surface. For solar scientists, this problem is especially serious because the Sun's poles are not fixed, solid landscapes. They are made of moving plasma and magnetic fields. To understand what is happening there, researchers must measure extremely subtle differences in light, motion, and magnetic direction. Yet near the edge of the Sun, those measurements become difficult. A magnetic field pointing toward a spacecraft may appear strong, while one angled sideways can seem weaker than it truly is. Plasma moving across the surface can be mistaken for plasma moving toward or away from the observer. Perspective does not merely blur the image. It can change what the instruments appear to measure. For decades, scientists found ways to work around this problem. They combined observations taken over time. They watched structures rotate into and out of view. They used mathematical models to estimate what might be happening beyond the visible edge. These methods taught us a great deal, but estimation is not the same as seeing. The first spacecraft to truly explore the high solar latitudes was Ulysses, launched in 1990. With the help of Jupiter's gravity, Ulysses left the ecliptic plane and passed over the Sun's northern and southern regions. Its journey transformed our understanding of the solar wind. It discovered that during quieter phases of the solar cycle, fast solar wind streamed outward from broad regions near the poles. It measured charged particles and magnetic fields in places no spacecraft had visited before. Yet Ulysses had a limitation of its own. It did not carry the kind of telescopes needed to photograph the solar poles in detail. Ulysses could travel through the environment above them. It could feel the particles rushing past and measure the magnetic field surrounding the spacecraft. But it could not look down and create detailed images of the surface and atmosphere below. It was like flying through a storm at night with instruments that could measure wind speed, pressure, and temperature, but without a camera capable of showing the clouds beneath you. So the poles remained partly hidden. Other spacecraft, including the Solar and Heliospheric Observatory and the Solar Dynamics Observatory, produced spectacular views of the Sun. They revealed the corona, tracked sunspots, and monitored eruptions almost continuously. But they remained close to the ecliptic plane. The same geometry continued to shape their view. This is one reason the first images from Solar Orbiter were so important. The mission was designed not only to travel close to the Sun, but also to gradually tilt its orbit. It would combine measurements taken directly from the surrounding space with images of the regions producing those conditions. For the first time, a spacecraft could begin connecting what left the poles with what was actually happening at the poles themselves. But changing orbital inclination near the Sun is extremely difficult. A spacecraft moving around our star already carries enormous sideways speed. To tilt that path, it must redirect part of its motion without losing control of its orbit or using an impossible amount of fuel. Solar Orbiter could not simply turn upward. Instead, it would have to reshape its path slowly, one gravitational encounter at a time, and for that, it would rely on a world hidden beneath thick clouds, circling closer to the Sun than Earth. Venus would become the staircase that allowed Solar Orbiter to climb out of the flat world of the planets. Solar Orbiter could not reach the Sun's poles by simply pointing itself south and firing its engines. In space, changing direction is often more difficult than moving faster. The spacecraft was already traveling around the Sun at tremendous speed, following the same broad plane as Earth and the other planets. To rise above or below that plane, it would need to redirect a large portion of its motion. Doing so with rocket fuel alone would require far more propellant than the spacecraft could carry. So instead of forcing its way out of the ecliptic, Solar Orbiter began a much slower and more elegant journey. It would borrow gravity from Venus. Whenever a spacecraft passes close to a planet, the planet's gravity bends its path. From the spacecraft's perspective, the encounter may last only a short time, but even a small change in direction can reshape the orbit that follows for months or years. Most gravity assists are used to speed a spacecraft up or slow it down. Solar Orbiter used them for something different. It used Venus to tilt. Each time the spacecraft returned to the planet, it approached along a carefully calculated path. Venus pulled on Solar Orbiter, rotating its orbit slightly farther away from the flat plane of the solar system. No single encounter was enough to reveal the poles. The climb had to happen gradually, 1 degree at a time, orbit after orbit. Imagine a moth circling a bright lamp inside a dark room. At first, it moves around the lamp at the same height, always seeing the light from the side. Then, with every pass, its path rises just a little. Slowly, the top of the lamp begins to come into view. Solar Orbiter was doing something similar, but on a scale of millions of miles. The spacecraft had launched in February 2020, beginning an intricate path through the inner solar system. It passed close to Venus and Earth, using their gravity to shape its orbit. It also moved nearer to the Sun than Mercury does during parts of its journey, allowing its instruments to study the star in extraordinary detail. But proximity alone was not the mission's greatest advantage. Other spacecraft had traveled close to the Sun. Parker Solar Probe had gone far closer, diving through the outer corona and surviving conditions no previous spacecraft had endured. Solar Orbiter was designed to offer a different kind of view. Parker moved like a fast explorer, passing through the Sun's atmosphere, sampling the particles and fields around it. Solar Orbiter carried a powerful combination of instruments that could both measure the surrounding environment and look back toward the Sun. It could observe the source and then sample what came from it. This made the spacecraft especially valuable for studying the poles. As Solar Orbiter's path tilted farther, the geometry began to change. Features near the southern edge of the Sun no longer appeared quite as compressed. Regions that had previously been hidden behind the star's curvature began to move into view. The change may sound small. In March 2025, Solar Orbiter reached a viewing angle of about 17 degrees below the Sun's equator. That is still far from hovering directly above the South Pole. From a human perspective, 17 degrees might seem like only a modest shift. But in solar observation, it was enough to cross an important boundary. For the first time, a spacecraft equipped with imaging instruments could see the Sun from clearly outside the ecliptic plane and examine the southern polar region from below. The spacecraft was not looking straight down. It was more like standing on the lower steps of a staircase and finally being able to see across the top of a high table. The full surface was not yet visible, but details that had always been hidden near the far edge were beginning to appear. And Solar Orbiter was carrying more than a camera. Its instruments were designed to examine different layers of the sun and different forms of energy. Some observed the visible surface, the photosphere, where light escapes into space. Others looked at hotter plasma higher in the atmosphere. Some mapped magnetic fields that the human eye could never see. Others measured the speed and composition of particles flowing past the spacecraft. Together, they allowed scientists to examine the South Pole as a connected system. The visible surface, the invisible magnetic structure, the atmosphere rising above it, and the solar wind that may eventually escape into space. This was essential because the sun's poles cannot be understood through a single image. They are not frozen landmarks. They are regions where matter, heat, rotation, and magnetism continually interact. A magnetic patch may emerge, drift, weaken, merge with another patch, or disappear. Plasma may rise along a field line and fall back moments later. Structures that appear stable can change over hours, days, or weeks. Solar Orbiter would need to watch these movements repeatedly. Its first elevated view was not the final destination. Future encounters with Venus were designed to tilt the orbit even farther, giving the spacecraft progressively better views of both poles. The mission was climbing toward a perspective that no imaging spacecraft had ever occupied. But even its first look south was enough to reveal something unexpected. Scientists had known that the sun was near the most active phase of its cycle. They expected the global magnetic field to be changing. They knew the poles were undergoing reversal. What they did not have was a clear view of how disorderly that transformation could appear. When Solar Orbiter turned its instruments toward the South Polar region, it did not see a single, clean magnetic domain. It saw a patchwork. Different instruments revealed different versions of the same place. One showed the glowing texture of the solar surface. Another traced hotter material in the atmosphere. And one transformed the invisible magnetic field into contrasting regions of color. Those colors showed opposing magnetic directions crowded together around the same pole. After years of orbital adjustments and millions of miles of travel, humanity had finally gained a new angle on the sun. And from that angle, the South Pole did not look like the end of an orderly magnetic field. It looked like the beginning of a transformation. On March 23, 2025, Solar Orbiter crossed an invisible boundary. The spacecraft had reached a position about 17 degrees below the sun's equator. It was not yet directly beneath the South Pole, and much of the polar region still curved away beyond the horizon. But for the first time, an imaging spacecraft was looking at the sun from far enough outside the familiar planetary plane to reveal the southern pole from a genuinely new perspective. The moment did not arrive with a flash or an explosion. There was no sudden signal announcing that humanity had entered a new chapter of solar observation. Solar Orbiter simply continued along its orbit. Its instruments pointed toward the star, while streams of data traveled quietly across space. Yet inside those measurements was something no previous generation had possessed: the first direct images of a solar pole taken from outside the ecliptic plane. At first glance, the images did not resemble the dramatic photographs people often associate with the sun. There were no enormous eruptions rising from the edge, no bright flare tearing through the corona, no dark planet crossing the glowing disk. Instead, the South Polar region appeared as a textured landscape of light, motion, and scientific color. And to understand what Solar Orbiter had found, scientists had to examine several different suns at once. One instrument observed the photosphere, the layer we commonly think of as the sun's visible surface. Of course, the sun has no solid ground. The photosphere is a glowing layer of plasma from which most visible sunlight escapes. Seen in this light, the polar region looked granular and restless. The apparent surface was covered by patterns created by convection. Hot plasma rose from below, released energy, cooled slightly, and sank again. Across the sun, This constant movement produces countless bright cells, separated by darker boundaries. Even when the star appears calm from Earth, its surface is never still. Another instrument looked higher into the solar atmosphere, observing extreme ultraviolet light emitted by plasma, far hotter than the visible surface below. In these wavelengths, structures shaped by magnetism became easier to see. Loops, arcs, bright patches, and faint extensions of plasma traced parts of the invisible magnetic architecture. The visible surface showed where light escaped. The ultraviolet images revealed how the atmosphere above it was being heated and guided. But the most unusual view came from the instrument that mapped the magnetic field. Magnetism itself cannot be photographed directly. Instead, scientists study subtle changes in sunlight produced when atoms are placed inside a magnetic field. From these changes, an instrument can estimate the strength and direction of the field in the region where the light originated. The measurements are then translated into a map. Different colors are assigned to magnetic fields pointing in different directions. One color may represent field lines directed generally toward the spacecraft, while another represents fields pointing away. These colors are not what a human eye would see while hovering above the sun. They are a visual language used to make an invisible force understandable. And at the South Pole, that language revealed a remarkable disorder. Rather than one dominant color covering the region, the map showed both magnetic polarities mixed together. Patches of one direction sat beside patches of the opposite direction. Small areas were scattered among larger ones. The pattern appeared fragmented, tangled, and unfinished. If the sun had behaved like a simple bar magnet, the South Pole should have been magnetically clear. One end would point one way, and the other end would point the opposite way. But the sun is not a simple magnet. It is a rotating sphere of conductive plasma. Different latitudes turn at different speeds. Hot material rises and falls. Enormous currents flow through its interior. Magnetic fields are stretched, twisted, transported, and sometimes broken apart. Near the peak of the solar cycle, this complexity becomes especially intense. Solar Orbiter had arrived at the South Pole during the most chaotic stage of its transformation. The old polarity had weakened, but it had not completely vanished. New magnetic material was continuing to arrive from lower latitudes. Opposing fields were meeting, canceling, and reorganizing. The South Pole was no longer governed by the magnetic identity of the previous cycle, but the next identity had not yet fully taken control. This was why both polarities could occupy the same region at the same time. The image was not showing two separate poles physically sitting together, nor was the sun somehow creating an extra North Pole and South Pole at the same location. It was showing a transition. A global magnetic structure was being dismantled patch by patch. To the human eye, the solar disk still looked whole. Sunlight continued to flood the solar system. The planets continued along their orbits. From Earth, the sun rose and set as it had for billions of years. But in the magnetic map, an enormous transformation was underway. Fields that stretched through the corona and far into space were changing their arrangement. The polarity that had dominated the South Polar region was fading. Its replacement was arriving in fragments rather than as one unified field. This made the first images important for more than their historical value. Scientists had long known that the sun's poles reverse near solar maximum. They had inferred the process from observations made near the ecliptic. They had watched magnetic patterns migrate toward the edges of the visible disk and used models to estimate what happened beyond them. Now they could begin watching the reversal from a more revealing angle. They could compare the visible structure of the surface with the magnetic map beneath it. They could observe the hotter atmosphere above. They could look for signs of plasma moving through the polar region and eventually connect those movements with particles escaping into space. The first look south did not solve the mystery. It made the mystery visible. And perhaps the strangest realization was that the disorder was not an accidental disturbance. The mixed polarities were part of the mechanism itself. The Sun could not build a new magnetic pole without first weakening the old one. Opposing fields had to arrive. Existing structures had to be cancelled or displaced. For a time, the region had to become less orderly before a new order could emerge. What appeared bizarre was, in fact, the Sun changing on schedule. But that raised a deeper question. If the South Pole was being rebuilt from countless scattered magnetic fragments, where were those fragments coming from? To answer that, we must look beyond the pole and follow the magnetic history of the entire star. Because every patch arriving in the south began its journey somewhere else, often inside a dark sunspot, far from the pole, years before solar orbiter was there to watch it arrive. At first, the magnetic map of the South Pole looked almost contradictory. One part of the region carried a field pointing in one direction. Nearby, another patch pointed the opposite way. Smaller fragments filled the spaces between them, creating a pattern that looked less like the end of a giant magnet and more like a mosaic, assembled from mismatched pieces. If the Sun were a solid object with a permanent magnetic field, this would be difficult to explain. A simple magnet has a stable north end and a stable south end. Its field lines emerge from one side, curve through space, and return through the other. The entire structure remains organized unless the magnet is physically altered. The Sun is different in almost every possible way. It has no rigid surface. It is made mostly of electrically charged gas, or plasma, that can flow, stretch, rotate, and carry magnetic fields with it. Deep inside the star, matter moves under enormous pressure. Near the visible surface, rising and sinking plasma produces a constantly shifting pattern of convection. And because the Sun is not solid, its equator rotates faster than its higher latitudes. The equatorial regions complete one rotation in roughly 25 Earth days. Near the poles, the rotation takes several days longer. That difference may seem small, but over months and years, it continuously pulls on magnetic fields embedded within the solar plasma. Field lines are stretched around the star, twisted into complex shapes, and gathered into regions of intense magnetic pressure. The result is not one permanent magnetic structure. It is a magnetic system that evolves. During quieter periods, known as solar minimum, the Sun's global field can appear relatively simple. One broad polarity dominates the northern polar region, while the opposite polarity dominates the south. Magnetic field lines extend outward into the corona in a pattern that loosely resembles the field around a bar magnet. This is the Sun at its most orderly. But even then, the surface remains active. Small magnetic regions continue to emerge and disappear. Plasma continues to move. Far below the visible layer, the processes that will create the next cycle are already developing. As the cycle advances, sunspots begin to appear at middle latitudes. These dark regions are not holes in the Sun. They look darker only because they are cooler than their surroundings, though they remain hot enough to glow intensely. Their lower temperature is caused by strong magnetic fields that interfere with the normal flow of heat from below. A large sunspot group may contain magnetic fields thousands of times stronger than the average field across the visible surface. And those fields rarely appear alone. Sunspots usually emerge in groups containing opposite magnetic polarities. One portion of a group may be magnetically positive, while another is negative. Between them, enormous loops of magnetic field rise into the atmosphere. As more active regions appear, the Sun's once simple global structure becomes increasingly complicated. Magnetic loops cross over one another. Fields become twisted. Some remain closed, with both ends anchored to the surface. Others reconnect and open outward into space. Energy accumulates inside these distorted structures until it is released through flares, eruptions, or smaller bursts of heating. This is why solar maximum appears so dramatic. But the sun's activity is not confined to the regions where sunspots are visible. Every sunspot group carries magnetic material that may eventually influence the poles. When a sunspot decays, its magnetic field does not vanish instantly. The large, dark structure breaks apart. Its magnetic flux is divided into smaller fragments and dispersed across the surface. Some fragments meet fields of the opposite polarity and cancel. Others survive. They are pushed by the constant motion of plasma, gathered along the boundaries of convection cells, and slowly carried away from the latitudes where they were born. Over time, a portion of this magnetic material migrates toward the poles. This is where the sun's global transformation begins to take shape. The old south polar field still exists, but magnetic fragments arriving from lower latitudes often carry the opposite polarity. As more of them reach the polar region, they begin to weaken the field already there. They do not arrive as one smooth wave. They arrive in patches. One fragment may be canceled almost immediately. Another may merge with nearby fields. A larger concentration may persist for weeks or months. The process is uneven, and the flow delivering these fragments can vary across the surface. The result is the mixed pattern seen by Solar Orbiter. Some regions near the pole still belong to the magnetic order of the old cycle. Others already carry the direction of the new one. For a time, both identities coexist. This transitional state can last much longer than a single observation. The sun's magnetic reversal is not a moment when the entire star suddenly flips like a compass needle. It is a gradual reorganization involving countless individual magnetic regions. One pole may reverse before the other. A pole may appear to reverse and then temporarily weaken again. The dominant polarity may shift back and forth as new magnetic material continues to arrive. From a distance, the process can look uncertain. But uncertainty is built into the transformation. The old field must be dismantled before the new field can become coherent. Magnetic fragments with opposite directions must meet. Some must cancel, others must survive long enough to accumulate. The pole becomes chaotic because chaos is the route through which the sun creates a new order. This is what makes the South Polar observation so valuable. Before Solar Orbiter, much of this process had to be reconstructed from measurements taken at an angle. The polar regions were compressed against the edge of the solar disk, where magnetic strength and direction were difficult to determine accurately. Now, researchers could begin separating the individual patches more clearly. They could observe how the magnetic network changed over time. They could compare where one polarity weakened and where the other began to dominate. And eventually, they could watch the South Pole settle into a more unified state. But that final state had not yet arrived. At the time of Solar Orbiter's first views, the sun was near the active peak of its cycle. Sunspots remained numerous. Magnetic fields across the surface were still complex. New flux continued to move toward the poles. The South Pole was not yet the stable endpoint of the cycle. It was a construction zone. Imagine rebuilding a vast city while its old streets are still in use. Some buildings have already been removed. Others remain standing. New foundations appear among the ruins, but the final pattern is not yet visible. The South Pole was undergoing a similar transformation, though its structures were made not of stone and steel, but of magnetic fields stretching through plasma. Every patch on the map carried part of the story. Some were remnants. Some were arrivals. Some were disappearing through cancellation. And some may have been the earliest pieces of the magnetic field that would dominate the next quiet sun. This is why the bizarre mixture at the pole was more than an unusual image. It was a record of time. The old solar cycle and the new one were both present in the same place, written into opposing magnetic directions. To understand how one could replace the other, however, we must look at the full rhythm of the star. The sun does not simply become more active and then calm down again. its global magnetic field weakens, reverses, and rebuilds in a cycle that takes far longer than the familiar 11-year rise and fall of sunspots. And when the process is complete, the entire sun will be magnetically inverted. The sun does not reverse its magnetic field in a single instant. There is no universal moment when every compass in the solar system would suddenly swing in the opposite direction. No sharp boundary separates the old magnetic sun from the new one. Instead, the reversal unfolds gradually, through years of rising activity, tangled fields, decaying sunspots, and magnetic fragments drifting toward the poles. To understand this process, it helps to begin during solar minimum. At this stage, the sun is relatively quiet. Sunspots are few. Major eruptions happen less often. The global magnetic field is more organized, with one dominant polarity in the north and the opposite polarity in the south. The structure is not perfectly simple, but from a distance it resembles a giant bar magnet. Field lines emerge from one polar region, curve through the corona, and return through the other. Broad areas near the poles may open directly into space, allowing the solar wind to stream outward. This is the closest the sun comes to magnetic order. But the calm does not last. Deep within the star, the next cycle is already developing. The sun rotates differentially. Its equator turns faster than its higher latitudes, and this unequal rotation continuously stretches magnetic fields around the star. Plasma moves through the interior in vast circulating patterns, while magnetic energy slowly accumulates. Over time, portions of the field become strong enough to rise toward the surface. They emerge as active regions. At the beginning of a new cycle, sunspots usually appear at middle latitudes, far from the equator. As the years pass, new sunspots tend to form progressively closer to the sun's equatorial region. When scientists plot their locations over time, the pattern resembles the wings of a butterfly. This beautiful shape is not merely decorative. It is a record of the magnetic cycle moving across the surface. As sunspot numbers increase, the sun becomes more active. Magnetic loops grow larger and more complicated. Solar flares become more frequent. Coronal mass ejections send vast clouds of plasma into space. The star approaches solar maximum. But beneath all this visible activity, something equally important is happening at the poles. Each sunspot group contains two main magnetic polarities. Because these groups are usually tilted slightly relative to the solar equator, the polarity on one side tends to sit a little closer to the pole than the other. This small tilt has enormous consequences. As the sunspot group decays, its magnetic field breaks apart. The fragments closer to the equator are more likely to meet opposite fields from the other hemisphere and cancel. The fragments positioned slightly farther poleward have a better chance of being carried toward the nearest pole. Over thousands of active regions, the effect accumulates. A steady supply of magnetic material with the opposite polarity begins to arrive at each pole. At first, it merely weakens the existing polar field. Then the old field approaches zero. This is the most uncertain stage. The pole may briefly contain no clear dominant polarity at all. Magnetic patches of both directions can appear in neighboring regions. The balance can shift from one observation to the next. One pole may complete the reversal before the other. The northern pole may weaken, reverse, and begin rebuilding, while the southern pole remains mixed, or the reverse may happen. The sun does not require perfect symmetry. Its two hemispheres can behave like related but independent systems. This is why the magnetic reversal is better imagined as a long season than a single day. The old magnetic order fades gradually. The new one arrives in pieces. Eventually, enough magnetic flux of the new polarity accumulates at the pole to become dominant. The patchwork begins to simplify. Opposing regions remain, but one direction slowly takes control. The pole has reversed. The north magnetic pole, now carries the polarity that once belonged to the south, while the south carries the polarity that once belonged to the north. The sun has turned its global magnetic identity inside out. Yet the familiar solar cycle is often described as lasting about 11 years. How can an 11-year cycle return the sun to a different magnetic orientation? Because the sunspot cycle and the full magnetic cycle are not exactly the same thing. After one 11-year cycle, solar activity rises and falls, but the polarities have switched. It takes another cycle for them to reverse again and return to their original arrangement. The complete magnetic rhythm therefore lasts about 22 years. This is known as the Hale cycle. A sunspot appearing in one hemisphere during one cycle will usually have the opposite leading polarity from a sunspot appearing in that same hemisphere during the next cycle. The orientation alternates, following the deeper magnetic rhythm of the star. From one solar minimum to the next, the sun may look similarly calm, but magnetically, it has become the inverse of what it was before. Only after a second cycle does the original orientation return. This 22-year pattern reveals something profound about the sun. Its activity is not simply a repeating rise and fall, like a tide returning to the same shoreline. Each cycle is linked to the one before it. The magnetic field inherited from a previous generation of sunspots influences the next polar field. That polar field may then help shape the strength and character of the following cycle. The sun carries a memory of its own past. But this memory is imperfect. Some magnetic fragments cancel before reaching the poles. Some are transported more quickly than others. Large active regions can contribute disproportionate amounts of flux. The northern and southern hemispheres can develop at different rates. The result is a cycle that repeats without ever being identical. One solar maximum may be intense and crowded with sunspots. Another may be weak. One reversal may unfold smoothly. Another may hesitate, with the poles shifting between competing polarities before settling. The basic rhythm remains, but the details vary. This is one reason predicting the sun is so difficult. Scientists understand the broad pattern. They know that decaying active regions help reverse the poles. They know that the polar field near solar minimum is connected to the activity of the next cycle. But they do not yet understand every step with enough precision to forecast the future perfectly. The South Pole seen by Solar Orbiter was suspended inside this uncertain interval. The old field had lost its control. The new field was still assembling. The mixed magnetic patches were not random decorations on a scientific map. They were individual pieces of a 22-year transformation taking place across the entire star. To understand how those pieces arrived there, we must now follow one of them. Imagine a small fragment of magnetism left behind by a dying sunspot. It begins far from the South Pole, surrounded by boiling plasma, scattered fields, and the remains of an active region. Its journey may last months or even years. Along the way, it may be stretched, divided, merged, or erased completely. But if it survives, that faint magnetic fragment may eventually become part of the new South Pole and help decide what the sun will do next. Imagine that we could shrink ourselves down until the surface of the sun stretched around us like an endless glowing ocean. There would be no solid ground beneath our feet, only plasma. Hot material would rise from the depths, cool slightly as it released energy, and sink again. Across the photosphere, countless convection cells would appear and disappear, their bright centers surrounded by darker boundaries. Somewhere within this moving landscape, a large sunspot group is beginning to decay. Only days earlier, it may have been one of the most obvious features on the sun. Its darkest central regions were wide enough to swallow the Earth. Powerful magnetic fields pushed through the photosphere, suppressing the upward flow of heat and creating the cooler areas that appeared dark against the brighter surface around them. Above the spots, magnetic loops arched high into the solar atmosphere. Some rose quietly. Others twisted around one another, storing energy until they erupted in a flare or launched plasma into space. But even the largest sunspots are temporary. Their edges begin to fragment. Bright channels of plasma cut into the darker regions. The organized field weakens, and the once distinct spots gradually dissolve into smaller magnetic patches. The visible sunspot disappears. Its magnetism does not. What remains is a scattered collection of magnetic flux, carried by the plasma at the surface. Our imaginary fragment begins here. It may be far smaller than the active region that created it, but it still carries a direction. Its field points either outward from the sun or inward toward it, depending on the polarity from which it came. The fragment is not a physical object floating above the surface. It is a region where the magnetic field remains concentrated inside the moving plasma. Wherever that plasma goes, the magnetic pattern is pulled and distorted with it. At first, the fragment is surrounded by many others. Some carry the same polarity. Some point the opposite way. They are pushed by convection, pulled into narrow lanes, and gathered along the edges of larger cells known as supergranules. A supergranule can span tens of thousands of kilometers. Plasma rises near its center, moves outward across the surface, and descends near its boundaries. The flow acts like a slow, relentless current, sweeping magnetic fragments toward the edges. From far away, this process creates a network. The interiors of the cells may contain relatively weak fields, while the boundaries become lined with concentrated magnetism. In ultraviolet images, these boundaries can appear brighter, tracing a constantly shifting pattern across the sun. Our fragment joins this magnetic network. It may remain there for hours or days, carried along by a sequence of cells that form, evolve, and disappear beneath it. The journey is not smooth. The sun's surface is constantly rearranging the path. A new convection cell may push the fragment sideways. A neighboring flow may split it into smaller pieces. Two fragments with the same polarity may merge into a stronger patch. But the greatest danger comes from the opposite polarity. When two magnetic regions with opposing directions are pushed together, their fields can reconnect and cancel near the surface. The magnetic structure changes, energy is released, and part of the flux disappears from the visible layer. If our fragment meets its opposite, its journey may end there. Much of the magnetic material released by dying sunspots never reaches the poles. The sun continually erases part of its own magnetic history. Near the equator, this cancellation becomes especially important. Sunspot groups in the northern and southern hemispheres often carry opposite arrangements of polarity. As their remains spread toward the equator, fragments from the two hemispheres can meet and destroy one another. But some fragments begin moving in the other direction, toward the poles. The flow responsible is far slower than the dramatic motion seen in a flare. It is not a violent current racing across the surface. It is a broad circulation, known as meridional flow. Near the photosphere, plasma tends to drift from lower latitudes toward higher ones. The speed may be only a few meters per second to a few tens of meters per second, depending on the location and the method used to measure it. That is slower than a person running. Yet the flow stretches across a star. Over months and years, it can carry magnetic flux through enormous distances. Our fragment begins to move southward. The change would be almost impossible to notice from one moment to the next. It is carried within a magnetic network that continually shifts around it. But when scientists track many patches over long periods, a larger pattern emerges. They migrate poleward. This process is helped by a small but crucial feature in the way sunspot groups appear. Most bipolar sunspot groups are slightly tilted relative to the solar equator. The spot leading in the direction of rotation usually lies a little closer to the equator, while the following polarity sits at a slightly higher latitude. This statistical pattern is known as Joy's law. The name sounds almost poetic, but its consequences are deeply physical. Because the following polarity begins slightly closer to the pole, it has a better chance of escaping cancellation near the equator and being carried toward higher latitudes. The difference in position may be modest within a single active region. Across hundreds or thousands of active regions, it becomes powerful. The Sun is not sending a random mixture of magnetic material toward each pole. On average, one polarity gains an advantage. That favored polarity is usually opposite to the field already dominating the pole. Our fragment may belong to that favored group. As it travels south, it joins more magnetic remnants from other decaying sunspots. Some were born weeks earlier. Others may have emerged on the far side of the Sun before rotating into view from Earth. Their paths converge only gradually. No single fragment is likely to reverse the South Pole. Together, they can. When the first of these patches reaches high latitudes, it begins interacting with the old polar field. Opposite fields cancel. The strength of the existing pole slowly declines. More flux arrives. The old polarity weakens further. At some point, the large-scale field may approach zero, leaving no clear magnetic direction in control. The pole becomes mixed, uncertain, and fragmented. This is the state Solar Orbiter began to observe. Our fragment, born inside a sunspot far from the pole, has now become part of the strange patchwork seen in the new magnetic maps. It may cancel one of the remaining pieces of the old polar field, or it may merge with other fragments of the new polarity, creating a larger and more coherent region. If enough similar flux continues to arrive, the balance begins to shift. The new polarity takes control. A fragment that once belonged to a temporary sunspot has become part of the Sun's global magnetic field. The scale of this transformation is remarkable. Sunspots may survive for days, weeks, or occasionally months, yet their magnetic remains can influence the Sun for years. A structure born in one active region may help erase a polar field, shape the next solar minimum, and contribute to the conditions from which a future cycle will emerge. In this way, the Sun preserves parts of its past while continuously destroying others. Every solar cycle is built from what survives the previous one. But there is a complication. For decades, scientists have estimated how quickly magnetic flux makes this journey by observing the Sun from near the ecliptic plane. At low and middle latitudes, the motion can be tracked reasonably well. Near the poles, the view becomes compressed. The fragments appear crowded together, and their true movement becomes difficult to measure. Solar Orbiter's new perspective is beginning to remove that distortion. And its early observations suggest that the magnetic network at high latitudes may be moving toward the pole faster than some previous measurements indicated. If that is correct, then the journey we have just followed may not unfold exactly as our older models predicted. The Sun's magnetic conveyor belt may be carrying its fragments with a different rhythm, and even a small change in that rhythm could alter how the old pole disappears, how quickly the new one forms, and how accurately we can anticipate the cycle that follows. The movement of magnetic fragments across the Sun is easy to overlook because it happens so slowly. A flare can erupt in minutes. A coronal mass ejection can throw billions of tons of plasma into space in a matter of hours. But the flow that helps rebuild the poles works on a much quieter timescale. It moves at only a small fraction of the speed of the most dramatic solar events. In some regions, the plasma drifts poleward at speeds comparable to a person walking or running. And yet, over the surface of the Sun, that gentle motion becomes one of the most important currents in the entire magnetic cycle. Scientists call it meridional flow. Near the visible surface, plasma tends to move from lower latitudes toward the poles. Deeper inside the Sun, There may be return flows moving in the opposite direction, creating vast circulation patterns that wrap around each hemisphere. The exact shape of this circulation is still being studied. It may not be a single, simple loop. Different depths may contain multiple cells. The flow may change with latitude, with time, and with the phase of the solar cycle. But near the surface, its role is clear enough to matter. It carries magnetic flux poleward. Imagine the photosphere not as a quiet, glowing shell, but as the surface of an enormous moving ocean. Across that ocean, countless magnetic fragments drift within currents, too broad to see in a single image. Some currents are local. Supergranules push magnetic fields toward the edges of their cells. Some are global. The meridional flow slowly moves the entire magnetic network away from the equator and toward the poles. Together, these motions form something like a hidden conveyor belt. It is not a solid belt, and it does not move at one constant speed. It is a pattern created by flowing plasma. Magnetic fragments join it, leave it, merge, split, and sometimes disappear. But over long periods, enough of them move in the same general direction to reshape the polar fields. This is one reason the speed of the flow matters so much. If magnetic flux travels poleward quickly, more of it may reach the pole before it has time to cancel with opposite fields along the way. If it moves more slowly, the fragments remain exposed to the chaotic surface for longer. They may be broken apart, diverted, or erased before completing the journey. The speed can therefore influence how much magnetic material survives, and the amount that survives helps determine how strongly the new polar field is built. This creates a delicate balance. A faster flow might deliver more magnetic flux to the pole, but it could also reduce the time available for different polarities to cancel at lower latitudes, carrying a more complicated mixture northward or southward. A slower flow might allow more cancellation before the fragments arrive. Yet it might also weaken the final polar field if too much flux disappears along the way. The outcome depends not only on speed, but also on the size, tilt, and timing of the active regions that produce the magnetic material. This is why the sun is so difficult to predict. The basic mechanism can be understood, while the final result still depends on thousands of individual events. One unusually large sunspot group can release an enormous amount of magnetic flux. If that region is tilted more sharply than average, it may send a stronger contribution toward the pole. If it appears near the equator, more of its field may cancel across the boundary between hemispheres. If it emerges late in the cycle, it may influence the polar field shortly before solar minimum. Each active region becomes one small decision inside a much larger system. For decades, scientists have tracked these motions using telescopes near Earth. They follow the magnetic network as the sun rotates and compare how features shift over time. From these patterns, they estimate the speed of poleward transport. But once again, the geometry becomes difficult near the poles. From the ecliptic plane, high-latitude regions appear compressed. A patch may move a great distance across the surface, while appearing to shift only slightly in the image. Fields can overlap along the line of sight. The changing angle also affects measurements of magnetic strength. This means that the final part of the conveyor belt has always been the hardest to observe. Solar orbiter is beginning to change that. From below the solar equator, it can look more directly into the southern high latitudes. The perspective is still not perfect, but it reduces some of the distortion that has affected previous measurements. By tracking the magnetic network over time, researchers can begin measuring how quickly individual features approach the pole. Early results suggest that the magnetic pattern at high southern latitudes may be moving poleward at roughly 10 to 20 meters per second. That range is not astonishing in everyday terms. A fast human runner could briefly move at a similar speed. But across the sun, sustained over months, It can carry magnetic structures hundreds of thousands of kilometers. And in some comparisons, the movement appears faster than earlier estimates derived from less favorable viewing angles. This does not immediately prove that old models were wrong. The observations cover a limited period. The flow can vary over time. Different techniques may measure different parts of the motion. More data will be needed, but even the possibility matters. If magnetic flux reaches the poles faster than expected, scientists may need to revise how they model the reversal process. The old polar field could weaken sooner. The new polarity could accumulate more rapidly. The timing of solar minimum might be influenced, and the field that remains when the sun becomes quiet could differ from what earlier forecasts anticipated. That field is especially important because it acts as a kind of seed for the next cycle. Near solar minimum, the polar magnetic field is stretched and transformed by the sun's internal motions. Over time, part of that field may contribute to the magnetic structures that later rise as new sunspots. The stronger the polar field at minimum, the more active the next cycle may become. This relationship is not perfect. The sun is too complex for any single measurement to predict everything. But among the forecasting tools available, the polar field remains one of the most valuable. That means the South Pole is not merely recording what has already happened. It may also contain information about what comes next. The magnetic fragments arriving there today were born in active regions from the current cycle. Once gathered and reorganized, they may help shape the cycle that has not yet begun. A field created from the remains of yesterday's sunspots could influence eruptions years into the future. The hidden conveyor belt therefore connects three different versions of the sun. The active regions of the past, the polar field forming in the present, and the solar cycle waiting in the future. But the magnetic journey does not end at the visible surface. As the new field gathers around the pole, it rises into the atmosphere above. There, it guides plasma through layers, where the temperature suddenly climbs from thousands to hundreds of thousands, and eventually to more than 1,000,000 degrees. Some of that plasma moves upward. Some falls back, and some may continue outward until it becomes part of the solar wind. To follow the story farther, we must now leave the glowing surface behind and rise into the restless atmosphere above the South Pole. The visible surface of the sun is not the end of the star. It is only the layer from which most of the light we see finally escapes. Above it lies an atmosphere unlike anything found on Earth. It begins with the chromosphere, rises through a thin and violently changing transition region, and then opens into the corona, the vast outer atmosphere that extends millions of kilometers into space. From a distance, these layers appear to merge into a single glow. Up close, they form a landscape of extreme temperature, motion, and magnetic structure. And above the South Pole, that landscape is especially difficult to understand. Near the photosphere, the temperature is roughly 5,500 degrees Celsius. Higher in the chromosphere, the plasma behaves in complicated ways, sometimes cooling and sometimes heating, as magnetic waves and small eruptions pass through it. Then comes the transition region. It is not a smooth shell surrounding the sun. It is irregular, folded, and constantly reshaped by magnetic fields. Across a relatively short distance, the temperature can rise from tens of thousands of degrees to several 100,000 degrees. Beyond it, the corona reaches temperatures of more than 1,000,000 degrees. This is one of the sun's oldest mysteries. Normally, moving away from a heat source should make the environment cooler. Yet the sun's atmosphere becomes much hotter above the visible surface. Magnetic fields are almost certainly responsible. They carry energy upward, twist, reconnect, and launch waves through the plasma. But the exact combination of processes that heats the corona is still being studied. The polar regions may hold part of the answer. Above the South Pole, the mixed magnetic fields seen at the surface continue into the atmosphere. Some field lines close back toward the sun, forming loops. Others extend outward. Along these pathways, plasma can rise, fall, accelerate, or become trapped. The result is not a quiet crown of light. It is a restless environment, filled with movement. Solar Orbiter studies this motion using an instrument known as SPICE, the spectral imaging of the coronal environment. SPICE does not produce a simple photograph. It separates sunlight into narrow spectral lines created by different elements, including hydrogen, carbon, oxygen, neon, and magnesium. Each of those lines is associated with plasma at a particular range of temperatures. By examining them, scientists can study different layers of the solar atmosphere. One spectral line may reveal relatively cooler plasma lower down. Another may trace hotter material closer to the corona. Together, they create something like a temperature-sensitive map of the region above the pole. But SPICE can also detect motion. When plasma moves toward the spacecraft, the wavelength of its light shifts slightly in one direction. When it moves away, the wavelength shifts in the other. This is the Doppler effect, the same principle that changes the pitch of a siren as it approaches and recedes. On the Sun, the shifts are extremely small, yet they allow scientists to estimate how quickly plasma is moving along the line of sight. From Solar Orbiter's elevated perspective, these measurements become especially valuable. Near Earth's viewing plane, motion around the poles is difficult to interpret. A stream moving vertically above the surface may appear mixed with motion across it. Features overlap near the edge of the solar disk. From below the equator, Solar Orbiter can separate some of those movements more clearly. The resulting velocity maps reveal a polar atmosphere in constant circulation. Some patches of plasma move upward, others move downward. In one region, material may be rising along a narrow magnetic structure. Nearby, another stream may be falling back toward the surface. The pattern is complex because the magnetic field beneath it is complex. Imagine standing above a dark ocean at night, while thousands of invisible currents move beneath the surface. Occasionally, a glowing line appears, revealing the direction of one current for a moment before it fades. The polar atmosphere behaves in a similar way. Magnetic fields guide the plasma, but the fields themselves are constantly changing. Small jets may shoot upward from the lower atmosphere. These events can be driven by magnetic reconnection, when neighboring field lines rearrange and release stored energy. Plumes may stretch far into the corona, forming long, faint structures above the polar region. Some of these flows last only minutes. Others can persist much longer. Together, they may contribute energy and material to the outer atmosphere. But not everything that rises escapes. Much of the plasma follows closed magnetic loops. It travels upward, cools, and eventually falls back toward the sun. From a distant perspective, this can resemble glowing rain descending through the corona. The sun is constantly lifting material into its atmosphere and drawing part of it back again. Above the South Pole, where the magnetic field is being rebuilt, that circulation may be especially changeable. As magnetic patches cancel or merge at the surface, the field lines above them can rearrange. A loop that was closed may reconnect with another structure. Plasma that was trapped may suddenly find a path outward. A stream moving upward does not automatically become solar wind. It must continue accelerating and avoid being pulled back by gravity. It must also travel along magnetic field lines that remain open to interplanetary space. This is why scientists are interested in connecting the Doppler maps with magnetic observations. If a region of upward-moving plasma sits above an open magnetic field, it may reveal one of the places where the solar wind begins. The measurements are still incomplete. Solar wind detected near Earth has already traveled millions of kilometers. By the time it reaches us, separate streams have mixed, collided, and evolved. It is like trying to determine the source of a river by examining the water far downstream. Solar Orbiter offers a chance to move closer to the beginning. Its instruments can watch plasma rising above the pole, while other sensors sample particles and magnetic fields around the spacecraft. By combining those observations, scientists may eventually trace some streams back to the regions that released them. For the first time, the South Pole can be studied not as an isolated edge of the Sun, but as a possible gateway, a place where magnetic fields shaped by the solar cycle rise into the corona, a place where plasma is heated, redirected, and sometimes released, a place where the Sun may begin sending part of itself into the space between the planets. Far above the mixed magnetic patches, some particles will fall back into the brilliant atmosphere. Others will continue outward. They will pass Mercury, cross the orbit of Earth, and travel toward the distant boundary of the heliosphere. To understand where they are going, we must now follow them beyond the corona and into the invisible wind that fills the solar system. The solar wind is invisible. It carries no color that human eyes can see, and it makes no sound as it crosses the vacuum of space. Yet at this moment, it is flowing past Earth. Streams of protons, electrons, and heavier ions are moving through the solar system, carrying traces of the Sun's magnetic field with them. They pass around planets, sweep over moons, and interact with every spacecraft traveling between worlds. This wind never completely stops. Even during the quietest phase of the solar cycle, the Sun continues to lose part of its atmosphere into space. Over billions of years, an enormous amount of solar material has escaped this way. But compared with the mass of the Sun, the loss is small. Our star is so vast that it can continue releasing this wind for billions of years without noticeably diminishing. What matters more is not how much material leaves. It is how far the Sun's influence travels with it. As the solar wind expands, it carries the magnetic field outward, creating an immense region known as the heliosphere. The heliosphere surrounds the planets like a vast, uneven bubble. Mercury lies deep inside it. So do Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Even the distant dwarf planets move through an environment shaped by particles and magnetic fields that began near the Sun. Far beyond Neptune, the solar wind finally slows as it encounters matter between the stars. There, the Sun's influence begins to weaken, and interstellar space gradually takes over. The exact shape of this boundary is not perfectly spherical. The solar system moves through the galaxy, and the surrounding interstellar environment presses against the heliosphere from different directions. But wherever its distant edge lies, the story of that enormous structure begins close to the Sun. And part of it may begin above the poles. For plasma to become solar wind, it must find a path outward. Many magnetic field lines near the Sun form closed loops. They rise from one location, curve through the corona, and return to the surface somewhere else. Plasma traveling along these loops remains connected to the Sun at both ends. It may rise high into the atmosphere, but much of it eventually cools and falls back. Other magnetic field lines are open. They remain anchored to the Sun at one end while extending far outward into the heliosphere. Along these open pathways, plasma can escape. The idea of an open magnetic field may seem strange. Magnetic field lines do not literally break and hang loose like wires. They are a way of representing the direction and structure of the field. But in the solar corona, some regions contain fields that extend so far outward that they effectively connect the Sun to interplanetary space. These regions often appear darker in extreme ultraviolet images because the plasma there is less dense and cooler than the bright surrounding corona. They are called coronal holes. Despite the name, they are not empty openings in the Sun. They are regions where the magnetic structure allows plasma to flow away more easily. During solar minimum, large coronal holes often form near the poles. From them, fast solar wind can stream outward at speeds reaching hundreds of kilometers per second. A particle moving that quickly could travel from Earth to the Moon in less than an hour. Yet the particle does not begin at that full speed. Somewhere in the lower solar atmosphere, it must first be heated, lifted, and accelerated. Exactly how this happens remains one of the central questions of solar physics. Magnetic waves may carry energy upward. Small reconnection events may release bursts of heat. Jets and plumes may inject plasma into open-field regions. Several processes may work together, varying from one part of the sun to another. The polar regions are especially valuable because they may offer a cleaner view of the fast wind's origins. During the 1990s and 2000s, the Ulysses spacecraft traveled through high solar latitudes and measured fast, relatively uniform wind flowing from the polar regions during quieter phases of the cycle. Those measurements transformed the scientific picture of the heliosphere. But Ulysses could not look down with imaging telescopes and identify the precise structures releasing the particles it detected. It could feel the wind. It could not clearly see the doorway. Solar Orbiter was built to connect those two sides of the story. Its remote sensing instruments can examine the surface and atmosphere. At the same time, its in-situ instruments can measure the particles and magnetic fields passing directly around the spacecraft. The challenge is timing. The sun rotates. Magnetic structures evolve. Solar wind does not travel in perfectly straight, isolated lines. Fast streams can catch slower ones, compressing the plasma between them. Separate flows may interact before reaching the spacecraft. Scientists must trace those particles backward, using their speed, composition, magnetic direction, and the changing appearance of the sun. It is a cosmic reconstruction. A stream detected in space may contain a chemical fingerprint linked to a certain layer of the solar atmosphere. Its magnetic polarity may connect it to a particular region. Its travel time may reveal when it left. By combining these clues, researchers can estimate where the wind began. Solar Orbiter's new view of the South Pole adds another crucial piece. It can observe the magnetic network from an angle that makes polar structures less distorted. SPICE can detect plasma moving upward through different temperature layers. Other instruments can identify open magnetic regions and follow their evolution. Then, farther from the surface, the spacecraft can sample what escapes. For the first time, scientists may be able to follow a nearly continuous chain, from a magnetic fragment carried toward the pole, to a field structure rising into the corona, to plasma heated and accelerated along it, to a stream of solar wind traveling into the heliosphere. The bizarre magnetic patchwork at the South Pole is therefore connected to something far larger than the pole itself. As the polar field reorganizes, the pattern of open and closed magnetic fields changes with it. New pathways may form. Old ones may disappear. The sources of fast and slow solar wind can shift across the star. The sun's changing magnetic identity reshapes the invisible environment surrounding every planet. Even Earth's protective magnetic field lives inside this greater system. Most of the time, the solar wind flows around our magnetosphere, compressing it on the day side and stretching it into a long tail behind the planet. During stronger events, the interaction intensifies, producing auroras and disturbances in near-Earth space. But the ordinary solar wind is not a catastrophe. It is the continuous breath of the sun, a quiet connection between the glowing atmosphere of our star and the dark space through which the planets move. And above the South Pole, where the old magnetic world is fading and a new one is forming, that breath may rise through plumes, jets, and open fields before beginning a journey toward the edge of the solar system. Yet those flows may not travel directly outward. The rotating sun can twist magnetic structures into spirals. Plasma currents may circle, shear, and interact above the poles, and some scientists have wondered whether a much larger pattern may be hiding there. A vast motion in the solar atmosphere. A polar vortex made not of clouds and weather, but of million-degree plasma and magnetism. On Earth, the word vortex usually brings to mind a hurricane. Clouds spiral around a calm center. Winds race in circles. Entire weather systems organize themselves around a rotating pattern that can persist for days. Other planets have their own polar vortices. Venus hides enormous twisting structures beneath its clouds. Saturn's North Pole contains a vast hexagonal pattern surrounding a powerful storm. Even planets very different from Earth can develop long-lived circulation near their poles because rotation, temperature, and fluid motion naturally create large-scale patterns. The Sun is not a planet. It has no solid surface, no weather in the ordinary sense, and no atmosphere made of familiar gases. But it does rotate. Its plasma flows. Its poles are surrounded by magnetic fields that can guide matter across enormous distances. So scientists have begun asking a natural question. Could something like a polar vortex exist above the Sun? The idea does not mean a single storm with a dark eye spinning above the South Pole. Any solar vortex would be made of electrically charged plasma and shaped by magnetism, not by clouds and atmospheric pressure. It might appear as a broad circulation in which plasma and magnetic structures drift around the pole. It could involve rotating plumes, spiraling flows, or bands of material moving in different directions at different heights. Or it might be less organized than the vortices seen on planets, a temporary pattern that forms, weakens, and reforms as the magnetic field changes. The possibility is especially interesting because the Sun rotates differently at different latitudes. Near the equator, the surface turns faster. Closer to the poles, it rotates more slowly. This differential rotation stretches and shears magnetic fields across the star. At high latitudes, the geometry becomes complicated, and the plasma above the poles may respond in ways that are difficult to detect from the side. From Earth, any circular motion around the pole would be compressed into a narrow region near the edge of the Sun. A stream moving around the far side might disappear from view. Another moving across the near side could appear to travel in the opposite direction. Several different layers might overlap. A true circulation pattern could be hidden inside the projection. This is one reason solar orbiters changing orbit matters. As the spacecraft climbs farther from the ecliptic plane, it will gain a more direct view of the high latitudes. Features that currently overlap may become easier to separate. Motions that seem horizontal from Earth may reveal themselves as part of a larger spiral. Scientists can compare images taken over time. They can track bright points, plumes, jets, and magnetic patches. They can use Doppler measurements to determine whether plasma is moving toward or away from the spacecraft. If the same broad pattern appears repeatedly, rotating around the pole, the case for a genuine vortex would become stronger. But for now, the evidence is not complete. The first elevated observations have revealed a dynamic polar atmosphere, but they have not confirmed one enormous, stable solar vortex. This distinction matters. The South Pole is already strange enough without adding certainty where none exists. What scientists have observed includes mixed magnetic polarities, shifting plasma, small-scale jets, and large magnetic structures extending into the corona. A single organized vortex remains a possibility to be tested. And perhaps that uncertainty is what makes the idea so compelling. For most of human history, we did not even have the angle needed to ask the question properly. Now, the first observations have opened a new region of the Sun, but only partially. Solar Orbiter is still looking from a relatively modest inclination. It has not yet reached a viewpoint directly above the pole. Future passes will tilt the orbit farther, allowing more of the hidden region to come into view. What looks like random motion today may later reveal a larger structure. Or the data may show that no stable vortex exists at all, that the polar atmosphere is too changeable, too fragmented, and too closely tied to the magnetic cycle to settle into one enduring pattern. Either answer would teach us something important. A confirmed vortex could reveal how plasma circulates above the pole and how magnetic fields transport energy through the corona. Its absence could show that the Sun's polar regions behave unlike planetary atmospheres, reorganizing too quickly to maintain a single long-lived flow. For now, the possibility remains suspended above the South Pole, a hidden motion waiting for a better angle, a pattern that may be there, turning quietly inside the million-degree corona, just beyond the limits of our present view. And even if no giant vortex is ever found, the search itself points toward a larger truth. The first images of the South Pole are not the end of a discovery. They are the beginning of a new way of watching the sun, a way that may eventually help us understand not only what is happening above the pole, but what the pole is preparing for the future. The sun's South Pole is not only a record of what has already happened, it may also be a preview of what comes next. Every solar cycle leaves magnetic material behind. Sunspots emerge, grow, decay, and scatter their fields across the surface. Some of that magnetism disappears through cancellation. Some is carried toward the poles. And by the time the sun returns to a quieter state, the surviving flux has been reorganized into a new polar field. That field matters because it may help provide the magnetic foundation for the next cycle. In this sense, the poles act like a bridge between one generation of solar activity and the next. The sunspots visible today help build the polar field of tomorrow, and that polar field may influence the sunspots that will appear years from now. This relationship gives scientists one of their most useful tools for forecasting future solar activity, the polar field precursor. The idea is relatively simple. When the sun approaches solar minimum and the polar fields become more stable, their strength can offer clues about the cycle that follows. A stronger polar field is often associated with a stronger future cycle. A weaker field may suggest a quieter one. It is not a perfect rule. The sun contains too many interacting processes for a single measurement to determine everything. But compared with many other forecasting methods, the polar field has repeatedly provided valuable information. The difficulty is measuring it accurately. From Earth, the poles sit near the edge of the solar disk, where perspective distorts both position and magnetic strength. The fields are often weak compared with those found inside active regions. Their signal can be mixed with surrounding structures, and the angle between the field and the observer makes interpretation difficult. Scientists compensate with models, long-term observations, and corrections for the viewing geometry. But every correction introduces uncertainty. If the polar field is stronger than it appears, then a forecast based on the measured value may underestimate the next cycle. If magnetic flux is moving toward the poles faster than expected, then the field may rebuild on a different schedule from the one used in the models. If one hemisphere evolves differently from the other, a single global prediction may hide important regional differences. Solar Orbiter offers a way to reduce some of these uncertainties. By viewing the poles from outside the ecliptic plane, it can measure magnetic structures from a more favorable angle. It can track how patches move across the high latitudes. It can compare the magnetic field at the surface with plasma motion in the atmosphere above. Over time, these observations may reveal whether our previous estimates of polar strength and poleward transport were incomplete. That question became especially important during solar cycle 25. Before the cycle began, several forecasts suggested it would be relatively modest. Some expected activity similar to the weak cycle that came before it. But as the years passed, Sunspot numbers rose faster and higher than many early predictions had anticipated. The sun produced powerful flares, repeated coronal mass ejections, and major geomagnetic storms. Auroras appeared at unusually low latitudes. Satellites experienced increased atmospheric drag and disruptions in near-Earth space. The cycle was not beyond anything the sun had produced before. But it was a clear reminder that forecasting our star remains difficult. There may not be one single reason the early predictions missed the final level of activity. The problem may involve several uncertainties working together. The polar field at the previous minimum may have been measured imperfectly. The transport of magnetic flux toward the poles may have behaved differently from what some models assumed. The sun's internal dynamo may contain variations that cannot yet be observed directly. Large active regions may also contribute unexpected amounts of magnetic flux, altering the cycle after it has already begun. The sun is not a clock with identical gears repeating the same motion. It is a turbulent magnetic system. Its broad rhythm is regular enough to recognize, but the details emerge from countless flows and interactions inside a star we still cannot see beneath the surface. This is why the mixed south pole is so valuable. It gives scientists a chance to watch the forecasting process while it is being created. The magnetic patches arriving there are not merely leftovers from the current cycle. They are contributing to the field that may help shape solar cycle 26. But the picture is not yet finished. Near solar maximum, the poles are weak, fragmented, and unstable. Their polarity may be changing, and the magnetic flux continuing to arrive can still alter the final result. The most useful measurements will come later. As activity far above the south pole of the sun, the transformation continues. The magnetic patches seen by solar orbiter are still shifting. Some weaken, some merge. Some are carried farther poleward by the slow movement of plasma across the surface. Others meet fields pointing in the opposite direction and disappear through cancellation. From one day to the next, the changes may seem small, but over months and years, the balance begins to move. The fragments of the old polar field grow fewer. The new polarity becomes more organized. What once appeared as a confused mixture slowly begins to favor one magnetic direction. The South Pole is rebuilding itself. There is no architect guiding the process. No central mechanism decides where each fragment should go. Instead, the new pole emerges from countless interactions across the entire sun. A sunspot forms far from the pole. Its magnetic field rises through the surface. The sunspot decays. Its remains are scattered by convection. Some fragments vanish, some survive. The survivors drift through the magnetic network until, eventually, a fraction of them reaches the high southern latitudes. There, they become part of something far larger than the active region that created them. A temporary sunspot contributes to a global magnetic field. A local disturbance becomes part of a 22-year cycle. A fragment born in one place helps transform a region hundreds of thousands of miles away. The sun rebuilds its poles from the remains of its own activity. As solar maximum passes, the number of sunspots will gradually decline. Major eruptions will become less frequent. The complicated fields surrounding active regions will begin to fade. At the poles, one polarity will slowly take control. The mixed pattern will become simpler. The global magnetic field will begin to resemble a great dipole once again, with one dominant polarity in the north and the opposite polarity in the south. The sun will move toward solar minimum. To a distant observer, this may appear to be a return to calm. But the quiet sun is not inactive. Its new polar field will already contain the history of the cycle that just ended. It will be shaped by which sunspots appeared, how they were tilted, how much magnetic flux survived, and how quickly that flux traveled toward the poles. Hidden below the surface, the magnetic system will continue evolving. the newly built polar field will be stretched, transported, and transformed. Eventually, parts of that magnetic structure may rise again as the active regions of a future cycle. The process that ends one cycle helps begin the next. Nothing is truly reset. The sun carries its past forward. Solar Orbiter will continue watching. Its journey is not complete. Future encounters with Venus will tilt its orbit farther away from the ecliptic plane. The spacecraft will climb toward higher solar latitudes, revealing more of the poles with less distortion. The views that seemed historic in 2025 may one day appear only as the first steps. From a greater angle, scientists may see how the magnetic patches circle the pole. They may track the final stages of the reversal more clearly. They may discover whether large-scale plasma flows exist above the polar regions. They may connect individual jets and plumes with the streams of solar wind traveling outward into the heliosphere. And perhaps they will find structures that the first observations could not yet reveal. The poles have been hidden for so long that we do not know how many questions we have not yet learned to ask. This is often how exploration begins. A spacecraft reaches a new place. The first images answer one question. Then they reveal 10 more. The South Pole was expected to help scientists understand the solar cycle. Instead, it also exposed the limits of our viewing angle, our magnetic measurements, and our models of how flux moves across the sun. It showed that a region can be familiar in theory and still look completely different when seen directly. For centuries, humanity studied the sun from one narrow band of space. We watched it from near the same plane as the planets. We measured its surface, followed its eruptions, and built increasingly detailed models of its interior. But the star always had another perspective waiting for us. A view from below. A view in which the South Pole was no longer compressed against the edge. A view that revealed not a simple magnetic endpoint, but a living boundary between two solar cycles. And perhaps that is the deepest meaning of these images. The sun often appears eternal. It has risen over every human civilization. It has warmed the oceans, powered the atmosphere, and made nearly every form of life on Earth possible. Against the scale of a human lifetime, it seems almost unchanging. But the sun is never still. Its surface boils. Its atmosphere expands into space. Its magni